Next, let's talk about classes and object. A class is a user-defined variable type that groups functions and data, and these functions and data can be accessed with the dot operator. A class serves as a blueprint for objects. Object-oriented programming is the style of programming that focuses around the use of objects and their blueprints, classes. Object-oriented programming has become an indispensable tool in terms of reasoning and in terms of structuring code in modern programming practice. So much so that any moderately sized, any moderately complex programming project will, to some extent, utilize some notions of classes and objects and ideas from object-oriented programming. In this course, we will be utilizing the PyTorch library heavily, and the PyTorch library is no exception. The features of the PyTorch library are organized around the use of classes and objects and also inheritance. In my view, I believe that everybody in their college years should spend some time taking not just a programming course, but also a programming course that teaches the basics of object-oriented programming. And I say this not just because object-oriented programming is utilized universally in programming practice, but also because object-oriented programming is not something you can fully appreciate with a few hours of study. So in this short tutorial video, I will not be able to adequately explain and motivate the uses of classes and objects, but what can we do? We have limited time, so I'll provide you with a brief overview of how to use classes and objects and inheritance. So here is a definition of a class in Python. So to define a class, we write class and then we provide the name of the class, we write colon, and then with indentation, we define the class functions one at a time. It's also possible to define class variables, which would in C++ or in Java correspond to static variables, but let's not talk about that today. Among the methods, there is this method called the init method. So the full name is __init __. So this function is called when an object is instantiated with this class. So this serves as the constructor, if you will, if you are familiar with the C++ or Java language. And then we have these other functions. So let's see how this is used. So once this class is defined, I can create an instance of this class. So this class is named complex, and the idea is that this class is used to represent a complex number. Now the idea of a complex number is an abstract thing, but it becomes more concrete when you have specific complex numbers with specific numerical values. So the class complex is a blueprint for an object, and when we instantiate, that's the word we use, when we instantiate the complex class, we create a complex object instance. So there is only one complex class, but if we create multiple complex numbers, then C1 is a complex number and C2 is also a complex number. To be more precise, C1 and C2 are reference variables referring to complex objects. So we've created two complex objects with the single complex class blueprint. This complex object is meant to represent 1 + 1 - 0.3i, and this complex object is meant to represent 5.5 + 2i. In the init method from complex, we take in the two inputs to the init method and assign them to instance variables. So in Python, instance variables are created basically on the fly within the init method in this way. There is no need to separately declare the instance variables within the class definition. So that's a distinction between the Python syntax compared to, let's say, C++ and Java. So once we create a complex number C1, then what we can do is we can do print C1.real, and that will return to us the real component of complex number C1. And we can do C1.imag, that will return the imaginary component of the complex number C1. More specifically, C1.imag will takes the reference variable C1 and accesses this complex object and retrieves the data member imag that was stored with this complex object. Now the benefit of having these type of classes, because so far what I've just demonstrated is that this complex object is a thing that contains a real number and a real part and an imaginary part. So those are just two numbers of the type float. So the complex object feels so far just like a concatenation of two numbers. Well, once we define the class in this way, and since we have defined these arithmetic operations, so we can do something like c1.mul c2. So this will take c1 and c2 and multiply it, and that multiply the two complex numbers according to this formula. And it will create another complex object. It will create another complex object, and we will have the reference variable c3 refer to this newly created complex object returned by this mul method, which is meant to represent multiplication. And then we can display the number, and this is the result. So when we multiply these two complex numbers, well, we get this thing. And we can do addition, we can do add, and we can do subtract. And when we are done with our arithmetic, if we want to display the number, then we can call the display method. And perhaps it would be better if I did this to f, point to f, to improve the formatting. So that way, if I do mul, it comes out quite nicely. So this is a pretty basic example, but let's see if we can improve this. So one room of improvement is that this notation, this syntax is quite cumbersome because we do c1 mul c2, but so we are calling the function called mul to perform multiplication. But that's not how we reason with when we think about complex numbers. We think c1 times c2. So we want to be able to use a more friendlier syntax. So the way we do that is we define what's called, there are several names. So some people call this magic methods. We do operator overloads, or another name is dunder methods. So these so-called magic methods are surrounded by double underscore. So underscore underscore init underscore 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 add underscore underscore. So these double underscores are referred to as dunder, which is short for double under. And dunder sounds like a silly thing to say, but it is used. It's a word used universally in the Python community. So I will also say dunder without any shame. So the list of Python magic methods is quite large, so I don't recommend going through them all unless you are really, really interested in fully understanding the Python language. But that's not necessary. But here I'll just show you a few examples. So here we have the dunder init dunder method, but we also have the dunder add dunder method. Previously we just had the add method, and because this method is not a dunder method, in order to call it, you just need to call it by its name. The method mul was just called by writing mul. But now we have two ways of calling these dunder methods. So when we want to multiply these two numbers, we can just do so in this way. So when we want to multiply two numbers, we just do c1 star c2, and that calls the dunder mul dunder method. Now this is equivalent to doing a dot dunder mul dunder c2. These two are equivalent. Here I'm explicitly calling the dunder mul method. Here I'm calling the dunder mul method using the operator star. It's the same thing, but this one is much more easier to see. Also, previously we had this display method, and this because without the display method, the class complex, if we just try to print out the class complex, we just get that, well, the thing that you're trying to print is an object of type class, because Python doesn't really know how should Python sort of reasonably format the data of class complex and print it out. How should Python do that? Well, we never explained how, so Python doesn't know. If we define this method called dunder str dunder, then this method gets called when we print a complex object. So now, instead of calling this display method, we can just feed the complex object into the print function, and it will do the printing automatically. Okay. So this is now much more the class now has become much more user-friendly by utilizing these magic methods, and something like this in C++ would correspond to operator overloading. In Python, there is no formal notion of private variables. So if you have a variable that begins with a dunder, so the variables can begin with dunder, and methods can also begin with dunder. They don't have to end with dunder, but if you start a method with or variable with dunder, then the convention is these methods and variables are understood to be private. And what I mean by private is private variables and methods should only be accessed within the class. It should not be accessed from the outside world. But this notion of privacy in Python is an informal one. It's just a convention that people are understood to abide by. So there's a distinction between that and, let's say, C++ and Python, where the notion of public and private access modifiers is formally baked into the language. So if you don't already know what private versus public access modifiers are, and if you don't know what the distinction of them, then don't worry about it. I'm just saying this for the sake of people who have had prior experience with those object-oriented languages. Okay, now here's a more sophisticated example, and this one is called. So this class is named polynomial, and it is its purpose is to represent a polynomial of real numbers. So here I'm not going to go through the details of this class definition. There's a lot going on, but I'm going to give you this as an example, and I'll let you play with it. So here we can define polynomials in this way. So here we have like a polynomial here, P1, the negation of that. So here we print P1. We have two polynomials. We print P1 and negative P1, so those have sign differences. We can define another polynomial. So we can define another polynomial. So we can subtract polynomials. We can add polynomials. We can't multiply polynomials because the dunder mult-dunder method has not been implemented. Maybe you can try that yourself, but this is something you can do. So one thing about this class is that here, this class comes with what's called a docstring. So the convention is that after you say class and the class name : by using the multi-line comment feature with the triple quotes, the convention is that you write a short text that describes what the purpose of this class is. So the docstring that I wrote is: this class implements a univariate polynomial. Arithmetic operations are plus minus are supported, and multiplication is an exercise. Now, so that was written as a docstring, and one way people can utilize this information is people can open up the file and actually just read this code as is. But another way people can access the docstring is by printing polynomial dunder doc dunder. So this is the common way of accessing the docstrings in Python, and as you can see, this is here. Okay. Here's another thing about classes. So you can, if you want to see what methods, what kind of functions, and what kind of data members a class, an object has, you can use the dict attribute or the dir function. So the dict attribute tells us what kind of functions are available. So this is a little bit messy to look at, but we can also print out the dir, and this will give us information about what kind of functions are available for us to use when it comes to this object. Duck typing is it's a tongue-in-cheek name of a somewhat serious programming philosophy. So let me explain what it is. Here's a function that's named sumAll, and it takes in as input a list, which I'm calling LST. Remember, you don't want to name your list because list is a reserved keyword in Python. So what we do is we take this list and then we add everything within the list. So initially we say return is equal to none, so we create the reference variable called ret, and then we iterate through the list. So for all elements within the list, If the return value is none, we set return to be equal to the element. Otherwise, we add element to the current return value, and then we return the final result. So let's take a look at this. So here I call the method SUMALL, the function SUMALL, with a list of these 3 numbers, and we get the total sum. And if I add in more numbers, then it's going to work as intended. Okay, so here we have a list of, in this example here, we have a list of numbers, but if you think about this carefully, if you look at this code carefully, there's nothing in this code or nothing in this function definition that presumes, that requires that the contents of this list be numbers. Because, and therefore, the sum numbers of a list does not fully describe the capability of this function. Rather, you can use this function called SUMALL if you can iterate through the elements of the list within a for loop. So in other words, if this thing is an iterable, and if you can use the plus operator for all elements of the list. Okay, so so for example, let's try this thing. All right, so if we have print SUMALL and then lst1, then what this will do is this is a list. This is a list of 2 strings, and if we call the method call the method SUMALL with it, then it will go through this, iterate through the list, and it will add the two strings. And what I mean by add is the plus operator. When you use it with strings, it performs concatenation. So we just concatenated all the strings. So another thing that we can add is lists. So here we have list 1 and list 2. We add the list. When you add lists, the meaning of that is you concatenate the list. So you take the entry elements of one list, and then you add the elements of the other list to the list to create a larger list containing the elements of both lists. So this is a concatenation of 2 lists. So now the result is a list of 4 strings, and when we call the method SUMALL, it's going to print out the concatenation of all 4 strings. But if we, let's say, instead do this, then this is, now the input is a list of 2 lists, and now when we add the 2 lists, that performs concatenation. So now we have the result is a list of 4 strings. And here in this function, we call the input LST, but there's really nothing that requires that LST be a list. It only needs to be something that we can use the for loop with. So I can provide a tuple. And it will have the same effect. And in fact, this is also demonstrated in the next example. So here we have 3 complex numbers, and then we provide a tuple of 3 complex numbers. When we sum them all, we get the total sum. And for that matter, we can also have a set, because a set is also an iterable. We can use a for loop with a set, so the result is we add all 3 complex numbers. So in order to use this function called SUMALL, we needed a thing, an input, that we can use a for loop with, and the contents of this thing, of LST, needs to be a thing that we can perform addition with, or something that we can use the plus operator with. In the context of logic, there is a form of reasoning called abductive reasoning, and it is concisely described by this quote. The quote goes, "If it looks like a duck, swims like a duck, and quacks like a duck, then it probably is a duck." Now, the choice of animal duck is probably reference to the name abductive reasoning, and the whole thing of duck typing is in reference is paying homage to this quote. In any case, I'm not at all familiar with sort of the field of logic at all. So if you're more interested in learning more about abductive reasoning, you can talk to your friends majoring philosophy. But in any case, in the context of programming, duck typing refers to the practice of caring about what the object can do rather than what it is. And this is something that can be done in Python, but not really at all in a strongly typed language such as C++ or Java. So in C++ or Java, when you compile your code, you need to ensure that the object is of a correct type so that your type safety is ensured. But in the context of Python, you just have a function and you just pass in a thing. And in order for the program to execute without any errors, it is necessary that this thing be capable of being executed a for loop on. And the things within this list need to be capable of doing this plus operation. So it's important in that sort of description, it was important what the object can do. We didn't really care about what the object is. It can be perhaps a complex number, it could be just a regular number, it can be a string, it can even be lists that we're concatenating with the plus operator. Whatever it is, if we can do plus with it, then it's okay, otherwise it's a problem. So that's a very, that kind of reasoning is focused on what the object can do, and that's the core idea of duck typing. So in the first week of this course, in the course Mathematical Foundations of Deep Neural Networks, we will be learning about gradient descent, the algorithm gradient descent. And in the algorithm gradient descent, so in the first week of the course Mathematical Foundations of Deep Neural Networks, we will be learning about the algorithm gradient descent. And in the algorithm gradient descent, if we apply the algorithm gradient descent to solve this optimization problem, we will get something like this. So this is the iterative gradient descent algorithm. And what's going on here is, I'll explain this this at symbol later on. But what's going on here is we're multiplying by the matrix A. So we're performing the matrix vector product A times X. And then we take the matrix transpose. So we form A transpose. And we're performing the matrix vector product with the matrix A transpose. So here, in this problem, A is a matrix, but in this code, A doesn't have to be a matrix. In fact, what A is not that important. In order for this code to execute properly, then if we ask what A must be able to do, and we're not asking what A is, the matrix A must be capable of performing a matrix vector product, and this in Python is implemented with the class function dunder matmul dunder. So this method must be implemented for this operation to be carried out when a vector x is provided. And then A must have an instance variable t such that A.t, this has to be a legal operation. So we need to be able to perform matrix vector products, and we need to be able to perform the transpose operation. So why does this matter? Well, there are cases where you can implement a matrix vector multiplication with A and A transpose efficiently, but forming the m by n matrix is inefficient. So examples of this includes a sparse matrix, the FFT, and the convolution. So these things, if you're not familiar what these are, don't worry about it. The convolution, you'll actually encounter this in probably homework 1 in the class. So you will be revisiting this notion in the first week of this class. So in these cases, you can provide objects supporting matrix vector products without directly forming a full matrix. So in this code, does A have to be a matrix? Well, not really. I mean, what A is actually not that important. What's important is what this thing A can do. It needs to be able to do these two things, and once that's provided, then this code will run without any errors. So the notion of duck typing is a very Pythonic thing. So the word Pythonic itself is a very Pythonic word, and it means that a certain type of code, a certain type of reasoning is very, it's made effective when you use the language Python, and it also means that people who like Python tends to appreciate that kind of reasoning or type of code. So in strongly typed languages such as C++ and Java, again, duck typing is mostly impossible because type safety is enforced very rigorously. And to achieve a similar effect, you are required to use inheritance or function pointers in these strongly typed languages. Next, let's briefly talk about inheritance. So because Python is not a strongly typed language, the use of inheritance is different from, let's say, other strongly typed languages such as C++ or Java. In Python, because the language is not strongly typed, inheritance is not used to provide type safety because the issue of type safety doesn't exist in the language Python. Rather, inheritance is utilized in order to reuse certain features that were implemented in another class and to build on top of it. Let's take a look at an example. So here I define a class called matrix, and the class matrix is used to represent a matrix. So for the dunder in a dunder method, we provide a tuple with the matrix dimensions, the height and the width, and then we within an array we provide a list of elements. And then we have a dunder add dunder method, a dunder mul dunder method, and a dunder str dunder method. So these methods are implemented, and let's see how this class can be used. So here M1 is so if we run, this is the matrix M1, this is the matrix M2, and when we perform the matrix product M1 times M2, we get this matrix. It's not that important that you understand the details of this matrix class implementation, although going through this code would be a decent exercise that can help you understand the notion of classes. But in any case, the point that I wish to make is that it took me some effort to implement these class methods. It wasn't terribly difficult, but it took me some time to write this code and to debug it. And if there's a circumstance where I can reuse this code instead of writing it again, I would like to reuse this code. Now let's define another class called square matrix. So a square matrix is a special kind of matrix, isn't it? Because for square matrices, we are able to compute a determinant, and we are also able to compute a matrix inverse, provided that the determinant of the matrix is non-zero. So a square matrix should have access to these additional methods. So what we do is we define the class square matrix, and we let the class square matrix inherit from class matrix. That way, all of these class methods are inherited by the class square matrix. In other words, all of these class methods are copied over to the class square matrix, so there is no need to redefine them again. And so once these methods init, add, mul, and str are all copied over, we can just implement the additional features, the det and the inverse functions, to make the square matrix be a class that has all the features that a class matrix has, but has these additional features called the det and inverse. By the way, here the actual algorithms for computing a determinant of a matrix and the inverse of a square matrix is actually somewhat complicated. So I didn't actually put in the effort to provide legitimate implementations of these functions, but I think you get the point. So in Python, the keyword pass is used as a placeholder. So here the function det is defined as a function, so you are required to provide some function body. And when you don't want to do that for, let's say, debugging purposes, or if you just want to have some sort of placeholder, then you can just write the keyword pass in Python, and this will tell, this signals to Python that yes, within the function body, we don't want to do anything. So this example illustrates a use case of inheritance where the goal is to copy over the implementations from another class and build on top of it. So even in Python, so for us more specifically, when we utilize the library PyTorch, we will be using inheritance to define classes representing neural networks. When we do so, we will, in addition to inheriting features from the parent class, we will also be overriding existing methods. So if you're already familiar with the issue of overriding, what overriding of a function is, then you understood what I meant. But if you're not familiar with the concept, don't worry about it. I'll tell you how it works when we define neural network classes. So the next topic is for loops and iterables. So when we write a for loop, we are able to iterate over the elements of container objects, but how does this actually happen? So let's take a look at a few examples. So for each element in this list containing 1, 2, and 3, if we print all of the elements, we get 1, 2, and 3. But it's not just lists that we can do this with. We can also do this with a tuple. So a tuple also has the same effect. We can also do the same thing with a set. So here, these curly braces are used to delimit a set. So here we have a set. We iterate through all the elements of a set. We can also iterate through the keys of a dictionary. So when we just write a regular for loop with a dictionary, we end up iterating over the keys. So we can do that. And we can also have a for loop iterating over characters in a string. So the string has characters A, B, and C, and we can iterate over the individual characters one at a time. Well, and also previously, we had seen something like this. So for index in range, so this will give us the index will range from 0 up to 4, and and the index can be therefore utilized as something like a for loop index. But what is this thing called a range? Well, if we just print out the range thing, it doesn't give us a list containing 0 up to 5. If we want that, we need to explicitly convert this thing into a list, and then we get the list containing 5 elements. If we just print out range 5, that's not a list. It prints this thing out. So we can try to probe what the type is. The type is class range. Well, if we print out, so what this is saying is that the output of range is an object of class range. So if we print out the directory of this range object, well, this is the list of functions that we can call with this range object. And note that there is a method called iter within the list. So the answer to the question of what can we use a for loop with? Well, we can use a for loop with what's called an iterable. So in Python, an iterable is an object that provides an iterator through the method iter. So the range object is an iterable because it provides the method dunder iter dunder. So here, if we took range 5, well, this is a range object. The type of it, when we probe the type, we get an object of class range. But if we call the method dunder iter dunder, then we get a range iterator object. Okay, so an iterable is a thing that can return an iterator. But then what is an iterator? An iterator provides access to the elements of the container using the method next. Okay, so let's try this. So here's a way to manually loop through the to the elements of range 5. So the first step is we retrieve an iterator by calling the method dunder iter dunder. And then we can do while true, and then we can loop through the elements one at a time. So when we call itr iterator a dunder next dunder method, that returns the next available element within the iterator, and this continues on until until we run out of elements and a stop iteration exception is thrown. So usually there's really no need to directly call the dunder iter dunder method manually. That's not how an iterator is intended to be used. Rather, an iterator is intended to be used within a for loop. So this example is an illustration. It's written for learning purposes, but rarely do you ever want to explicitly call the dunder iter dunder method. But if we continue with this learning process, then we can manually call the iter method and the next method and simulate the effect of having a for loop with this while loop with a try except block. So here we create a range object, and then we retrieve an iterator from this range object by calling the dunder iter dunder method, and so we have itr, that's the iterator. And then within the while loop, what we do, let's execute this first. So we print out. So the effect of this while loop is we print out all the elements within this this iterable, this range object. If I change this to 10, it works this way. And I can also change this to like some arbitrary list, and it will work exactly the same way. I can also make this a string, and it will work the same way. So what's going on here is we call the dunder iter dunder method to get an iterator. And then when we get an iterator, to access the individual elements one at a time, we call the dunder next dunder method. But this method call, as we saw before, will throw an exception. It will cause an error if there are no more elements to retrieve. So we put this in a try except block. So this try except is similar to a try catch block in other programming languages. So we try this thing, and if no error happens, then we just happily print the result. If an exception is thrown, and if the exception is a stop iteration exception, then it's caught by this except block, and then we break out of the while loop. So in this tutorial, I'm not going to spend time on discussing exceptions and how the try except block works. So if you're not already familiar with the notion of exceptions and try catch blocks, then I'm sorry, this example probably did not make too much sense. But I wanted to give you a rough idea as to what it is, how exactly the for loop is working, and what you can use the for loop with. You can use the for loop with an iterable. And when you use, and iterables are objects that provide a method dunder iter dunder method that you can call in order to retrieve an iterator, and the iterator can be used to access the elements one at a time. So as I discussed, you usually don't want to be calling the dunder iter dunder method yourself, and you usually don't want to be dealing with the iterator yourself, and you don't want to be calling the next method yourself. But if you have to, then instead of explicitly calling the dunder iter dunder method, you can call the iter function. So you can you can call the iter function and provide as input an iterable to retrieve the iterator. So these names are a little bit confusing, but hello, this string is an iterable, and an iterable is capable of producing an iterator when you provide it as input to the iter function. So then the iterator, the thing that does the iteration, the iterator, we can then pass that into the next function to retrieve the next element that the iterator is meant to access. So these two programs are, these two loops are exactly the same. Well, here the difference is this part. So here the iterator is the range object. Here the iterable is the range object. Here the iterable is a string. But otherwise, these two loops are exactly the same. So at the beginning of this tutorial, I mentioned that Python generators is a concept that we will be covering. So let me correct myself. When I said Python generator, I really meant to say iterators and iterables. So a generator in Python is a related but different concept. It's an interesting concept, and it is a generator is a specific instance of an iterable. In any case, it was Python iterators and iterables that I wanted to talk about, so let's move on. To further understand the notion of iterables and iterators, let's build a custom iterable. So the iterable that we will be creating is sentence, so we define it as a class sentence, and the iterator associated with a sentence object will be created by the class sentence iter. Before we look at the class definitions, let's first take a look at the result of using these iterables. So we create a sentence object by passing in a sentence separated with words separated with spaces. So that's called my sentence. And if we use it with a for loop, then the for loop iterates through our sentence. For each word, we print out the word, and the word is "this is a test." So here we could also just put this here without having the my sentence separate a variable name, and this would have the same effect. Okay. Another way to use this iterable is to have my sentence object. So my sentence is a reference variable referring to a sentence object with this string passed into the init dunder method. So we retrieve the iterator from this iterable. So we call that a sentence iter. And then with the iterator, we can retrieve the next element within our iterator one at a time. So let me comment out this for loop. So we retrieve one word at a time. This is a test, and then once we run out of words, once we run out of elements from this iterator, then if we call the next best method once more, we get a stop iteration exception. Okay, so let's see how this is done. So the class sentence is a very simple class. So it takes in the dunder init dunder method of class sentence, takes in a string as input. So this input is stored as a class, a data member, as a class attribute in this init method. And then when the dunder init iter method is called, so sentence is an iterable. An iterable is capable of returning an iterator. And the iterator is returned when the dunder iter dunder method is called. So here in this dunder iter dunder method, a sentence iter object is created, and when this object is created, we pass in the sentence, the string that was passed in, and this object that was created with this the object that was instantiated here is returned as the iterator. So then the sentence iter has to be a class. So let's define that class here. So the class sentence iter has a dunder init dunder method. So it takes in as input a string, and then it keeps a list of those words as a list. So the sentence.split method, this returns a list of strings, separated words that separated by spaces. Okay, so in this test example, the words were separated by spaces, so the split method splits the sentence based on where the spaces are. And then the dunder init dunder method also initializes this data member index to be initially equal to 0. Then once this, so this dunder init dunder method so remembers the sentence, it remembers the index, and then that iterator is returned when the dunder init dunder method is called, as it is here. Then when the next method is called, well, what this does is, if first the next method checks whether there are any words that are left to be returned, and if not, if we've exhausted all the words, then a stop iteration exception is raised. So otherwise, we have this index, we return the current word, and also we increment the index for the next time. Okay, then going back to this example. So here, when we have sentence and then we provide a string, this is calling the dunder init dunder method of class sentence. So an instance, an object of type sentence is created, and when that happens, this function is getting called. And then at this step, when we extract an iterator from the object of type sentence, this method is called. And when this method is called, a sentence iter object, so an iterator is created and the iterator is returned, and it is and then stiter, the reference variable stiter is made to refer to an iterator. And then when we call the next method, well, then that calls this method from the iterator object, and every time the index is checked, and if there remains a word to be returned, then a word is returned. And every time the next method is being called, this self.index, this index integer is being incremented by value 1 every time this is being called, and eventually we run out of words. In other words, this condition evaluates to be true, and at that point the next method raises a stop iteration exception, and the program crashes. Okay, so this was an example, a basic example of creating a custom iterator. And here's another example. So in this example, I want to point out that iterables, or to be more precise, iterators do not have to end. So, and if an iterator does not end, then its use is going to be slightly different. But let's take a look at this example. So here we have a class named Fibbo, and then we have Fibbo iter. So we'll look at this in just a second, but let's first look at how it is being used. So for the numbers in this iterable, or the iterator, what we do is we check if the number is bigger than 100, and if so, we exit the for loop, otherwise we print out the number. So this is the sequence of Fibonacci numbers, and well, it looks like this, and a loop structured in this way might be useful if you don't necessarily want, let's say, the first 10 numbers, but maybe you want the numbers until you want all numbers that are below 100. So if I change this to, let's say, bigger than 300, then we get all the Fibonacci numbers less than 300. So let's see how this works. So the class of Fibo is defined in this way. So the dunder init dunder method is defined, but it's defined to not do anything. So the function body is just pass. And the iter method, which is called to return an iterator, is defined by just returning an instance of Fibo iter. Okay, so we have class Fibo iter. A Fibo iter initializes a starting index, and there's no notion of ending. So the Fibo iter class will never it will never raise a stop iteration exception. So when the next method is called, we increment the index by 1, and if the index is initialized to be 0, so at the very start we have the index equals to 0, in that case we just return 0. Now if the index is 1, then we set the previous to be 0 and the current to be 1, and then we return 1. So that would correspond to this case. And by the way, this data member, this field, this data attribute, prev and cur for the class Fibo iter, was not defined. It was not defined in the dunder init dunder method. It was not defined outside of the class. It was just created here on the fly, and that's fine with Python. You can dynamically create data members in Python, and that's perfectly fine. Okay, so when in the 0th case, when the index is 0, we return 0. When the index is 1, we return 1, but we keep track of 0 and 1 as the previous and current values. And then after that, then the next result is previous plus current. So and next is, by the way, a reserved keyword, so we don't want to use that as a variable name. So I'm going to rewrite that as nxt instead of next. So the next element is the previous plus the current one, because as you can see, 3 plus 5 is equal to 8, and 5 plus 8 is equal to 13. That's the definition of the Fibonacci sequence. And so we compute the next one that is to be returned, and then we update the previous and the current. So the previous, what is now what we had currently, and the current is what we now have as next. And then we return the current number. But by the way, on here, the way this is structured is we are performing essentially 2 assignments in one line. So 0, 1 is a tuple, and prev, cur, that's also a tuple. So we are assigning a length 2 tuple to a length 2 tuple, and that way we are able to write 2 assignments in one line, and I think that's a much more cleaner way to write this. Also, as an optimization, or we can also do something like this. So this would result in the same exact code. Perhaps it would be more clear to do this, but so we can actually just do this in one line, and that's also fine. But I think it's more clear to do this. Okay, so here, if I don't have this condition, then the for loop will just go on forever, and you can see it's right now. Well, it went on forever, and then some upper limit as to how large numbers can be was reached, so the program crashed. But if you have an iterator, an iterable or an iterator that doesn't end, then you want to have some sort of mechanism that allows. Let me interrupt. Okay, I interrupted the kernel. So you want to have some sort of mechanism to terminate. When you use an unending iterator, you want to have some sort of mechanism to terminate the for loop. Okay, so those were 2 examples of custom-built iterables. Now, when you were looking at this code, so for this code, the iterable and iterator were separate classes, and here the iterable and iterator were separate classes, and I wrote it this way to make the point that an iterable and iterator are two distinct classes, or at least they can be two distinct classes. But you might have had the feeling that the code is somehow, the way it's written is somehow inefficient. It's not the code structure is not optimal. Well, that is true. So in some cases, when you write an especially complicated iterator and iterables, you sometimes do want to have separate classes for the iterator and iterables, but in many cases, it's actually just fine to combine those two objects into one. So here, I've restructured the sentence class. So the sentence class now has these initializations, and then when the iter method is called, it returns itself. So now this sentence class also has a dunder next dunder method, and now the two classes are combined into one. The sentence both serves the object of class sentence serves as both the iterator, the iterable, and the iterator at the same time. The same can be done with the class Fibbo. So now an object of class Fibbo is both an iterator and iterable at the same time. And combining the iterator and iterable is quite common practice in Python. So this would be better style, but I withheld this version from you before, just to make the point that the iterable and iterator are two distinct things. But once you've understood that, then I want to at the same time tell you that the two can be combined. By the way, this example was this sentence example was inspired by this guy Corey Schaefer's YouTube channel. So this guy this guy has some pretty good Python tutorial videos. So you can check out his videos if you. The next topic is context manager and the with statement. So a context manager is an object that defines the runtime context to be established when executing a with statement. Okay, so the context manager provides an enter method, a dunder enter dunder method, and dunder exit dunder method, and you can use context manager with statements. Okay, so let's take a look at an example. So here's a very bare bone example. We have a class named C manager, so this is to be used as a context manager. The class has a dunder init dunder method. It's not mandatory that a context manager has a dunder init dunder method, but you usually do want a context manager to have an initializer. Then the class has a dunder exit enter dunder method and dunder exit dunder method. So you can use a context manager with a with statement. So you write with context manager and then colon, and then you indent to have your code belong to the context established by the with statement. So let's execute this and see what happens. So this is just a class definition, and then so this is the start of the main code. So we start the with statement. So this when we do C manager open close parentheses, this creates an object. It instantiates an object of class C manager. So this dunder init dunder method is called. So manager constructed. So this is the first output message, and then we enter the context established by the with statement. So what that means is the dunder enter dunder met gets called. So okay, so this message, this code is executed. This context begins. A string is printed out, and then the body of the with statement gets executed. So let's do stuff here, and then when we exit the context established by the with statement, this dunder exit dunder method gets called, and we print out this stuff. And as you can see, this happens. Okay, so that's the basic mechanics of how a context manager and a with statement works. Now, at this point, you're probably not convinced as to why this is a useful thing. So let me show you a useful example. So let's say we have some code, and we want to measure how long this code takes. So one way to measure the time it takes to execute a block of code is to insert timer codes before and after the block of code. That's a possibility. But that's slightly cumbersome, it's slightly error prone, and it's also slightly repetitive. So instead what we can do is we can define a context manager called timer. So this class timer has an init method. It takes in as input a certain text description. We store that as a data member. And then when we enter the context, we keep track of the time. We take a timestamp, and then when we exit the context, we get the time. And then since we stored the time when we entered the context manager, we can take the difference. So we compute the difference, and that's the time it takes to execute this block of code. So let's execute this and see what happens. Okay, so here when we start the with statement, the timer object is created. So this text description of the timer is stored as a data member. And then as we enter the context established by the with statement, we call the dunder enter dunder method. We record the time at that point. And then this thing takes some time, so that gets executed. And then once we are done, we execute the dunder exit dunder method, and that prints out the time it took to execute this code. So this example, the list comprehension example, took this many seconds. By the way, this example could be made a little bit more cleaner if we use the F string. So let's refactor our code. Okay. Okay, so and let's do this. All right, now our code is much more cleaner. The F string is a much more cleaner way, and the formatting is now much better. Next, let's talk about NumPy. So NumPy is a numerical computation library for the Python language. When performing numerical computation, NumPy arrays are far superior than raw Python lists. Remember, the language Python comes with a basic data type lists. So since numerical computation is usually done with vectors and matrices, it's possible to put all the numbers in a list and then perform computation directly without relying on the NumPy library. Now, while that is possible, doing so will result in much less readable code, and it will also result in a lot of inefficiencies. So when you want to perform numerical computation, the NumPy library is far more effective. Now this course, however, is about deep learning, and to perform deep learning computation, we will be using the PyTorch library rather than the NumPy library. So why am I talking about the NumPy library? Well, the PyTorch library is designed as at least roughly an extension of the NumPy library. So a lot of features that are available in NumPy are available in PyTorch, and a lot of these syntactical features also carry over. So for this reason, we'll first learn about NumPy and how it interacts with the PyTorch library after. Okay, so in NumPy, we can create arrays, and there are several ways to create arrays in NumPy, but the most basic one is the np.array function, which creates a NumPy array from the Python list. So more specifically, we'll be importing the NumPy module as np. So instead of saying np array, perhaps I should have said NumPy array. In any case, so here, if I execute this, we created 3 NumPy arrays. Let's print them out and observe them one at a time. Okay, so this A is a NumPy array with these numbers, but when we create a NumPy array, we are also able to specify data types. So here, this NumPy array contains integers, but more specifically, the data type is are integers with 32-bit representations. And then let's print out B. So the array B is a NumPy array with containing 3 numbers, but these 3 numbers are to be interpreted as floating point numbers. And the specific data type is a double precision, so 64-bit representation, floating point numbers with 64-bit representations. And C, and it's also possible to, by having a nested list, it's possible to create a 2-dimensional array in NumPy. So you could interpret this as a matrix, but and it's also possible to not specify the data type, in which case it's going to be inferred automatically. Okay, so now let's. So now that a NumPy array has been created, we can query some information about the NumPy array. So If I want to query the dimension of a NumPy array, I can print out a C n dim. So this is the number of dimensions. So C is a two-dimensional array. We can interpret it as a matrix, so it has 2 dimensions. If we print out C, we would have to index this array with 2 indices. That's why it's 2-dimensional. But if we print out, let's say, query the number of indices for A, well, this NumPy array is just like a sequence. We can interpret this as a vector, and there's only 1 dimension for this array. Okay, and let's see. So we can also look at the shape of a NumPy array. So let's first look at the shape of A. The shape of A is 3, 1. So 3, nothing. And we get this output because, so what is this? Well, this is actually a tuple of length 1, right? So the parentheses, it tells us that it's a tuple. The comma after nothing, that means 3 is the only element of this tuple. Now, the shape of this array is 3, nothing, because all shapes of a NumPy array are returned as tuples. So for example, the shape of this array C it's 2 by 3. It's a 2 by 3 array, whereas A is a 1 by nothing array. So for the sake, it would be reasonable to return the dimension of this 1D array as just a regular number rather than a length 1 tuple. But for the sake of consistency, the shapes are returned as tuples, regardless of whether it's 1-dimensional or multi-dimensional. Okay. Now we can also probe the number of elements. Look at the number of elements in a NumPy array. So array A has 3 elements. Same is true with B, but C has, as you can see, 6 elements in total. And we can look at the type of the elements of this array. So, the data type of the array A is int32. The data type of B is float64, and the data type of C is also float64. So when you create a NumPy array, and if you don't specify the data type, then the inferred data type is, the data type is inferred from the data. So let's take a look at this example. In this case, because the input data only consisted of integers, the inferred data type was int32. So sometimes you want to be careful with using this default inferred data type. So it's convenient to not explicitly specify the data type. Not typing anything is convenient, but more convenient than typing in additional information, but which is nice. But sometimes the NumPy array dunder init dunder method might infer the wrong data type. So you want to be a little bit careful with what data type the NumPy array is being constructed with. Okay, and then we can also probe the size of the elements in bytes. So let's print the item size of A. So A is a NumPy array with int32 data type. That means every element of this NumPy array, so this NumPy array contains 3 numbers represented as 32-bit integers. So 32-bit means 4 bytes. Right? Because one byte is equal to 8 bits, so 32 bits is 4 bytes, so that's what this is saying. So each item has 4 bytes. Now in contrast, if we look at the item size of B, B is an array that contains 3 numbers represented in 64-bit floats. So 64 bits, that's 8 bytes, so each item size is 8 bytes. Now for array C as well, the item size is equal to 8. So the total size of the NumPy array in bytes can also be retrieved. So a.n bytes, so that's the total size of the NumPy array in bytes. So A is a length 3 array, contains 3 numbers, each occupying 4 bytes. The total size is 3 times 4 equals 8 bytes. The total size of array B is 24 bytes because there are 3 numbers each occupying 8 bytes. The total size of C is 48 bytes because there are 6 numbers each occupying 8 bytes. So when discussing NumPy arrays, I want to define my terminology. So the word array in the context of this lecture, and actually throughout this entire course, will refer to a group of numbers, an organization of numbers that with 1, 2, 3, or more dimensions. In contrast, a matrix will specifically refer to a two-dimensional array. So a two-dimensional array can be understood as a matrix. A one-dimensional array can be understood as a vector. But when I say array, that can be just any dimension, any size. And in fact, in this course and in deep learning in general, the use of three-dimensional and four-dimensional arrays are quite common. So we do want to become accustomed to working with higher dimensional arrays. Okay. Now the reason we'll be using four-dimensional arrays is because, well, in PyTorch, what we get is when we process images, we will have the x dimension, the y dimensional, because an image is a two-dimensional data. But then there's also the color channel, or more generally just the feature channels. So there's that dimension, and then there's a final fourth dimension called batches. So that's something we will learn about later in the class. But if you add batches, because an image is usually understood as a three-dimensional data, but we have this additional dimension called batches, so we get four-dimensional arrays. Now, if in this course, we're not going to be dealing with video data, but if one were to work with video data, then you would get five-dimensional tensors, five-dimensional arrays, because a video, a color video is often interpreted as a four-dimensional data, but then if you have batches, then you'll have a five-dimensional array. So these higher dimensional arrays are common; they're used all the time. So we want it's not sufficient for us to become accustomed to two-dimensional data structures. That's not enough. We need to become comfortable with three- and four-dimensional arrays as well. Okay, so here we create. Here are some basic array creation commands in NumPy. So NumPy zeros at 0, 2, 3. So this creates. So this creates just a 2x3 array of NumPy 0. And by the way, let's take a look at dtype. So the dtype of the zeros is by default float 64. And by the way, in my view, this was not at all obvious because zeros can also be perfectly represented well with int. So this could have been int 32, but the default behavior when you call the zeros method in NumPy is to create a NumPy array with data type float 64. Okay, and another one is NumPy ones. So let's see. So here we create an array with populated with all ones, and the dimensions are going to be 4 by 2 by 2. So if we print it, when you have these higher dimensional arrays or dimension higher than 2, printing the array is a little bit awkward. But the way this works is, so here we have 4 printouts. So those are the 4 values, 4 indices corresponding to this first dimension. And then, so with this being 0, we print out the 2 by 2 array. With this being 1, we print out the 2 by 2 array, and so on and so forth. So the printing is always a little bit awkward, but what can you do? This is already a 3-dimensional array, so this is the best one can hope for. What's the data type here? Data type is float 64. Let's see, what's the command? So let's get the number of elements, a.size. So there are 64 elements, and that's of course because the dimension is 4 by 2 by 2. So if we multiply them all, we get 16. So there are 16 elements in this NumPy array. Okay. All right. So if we do NumPy ones, so print. So here, if we do this, right, so note that there's a difference in the syntax. So as input to this, or I guess this is the 0 function, but for the 1 function. So here, we are providing a single tuple as input for the ones, in this case, a function. And here, we're providing the value 5. So this is not a tuple. It's just a single number as input to the ones function. Now, this actually turns out, so if we want to write something that corresponds exactly to this this syntax, we would be required to provide a tuple of length 1, and this actually produces the same result. But I'm letting you know that these two are, so this line and this line are, I guess the meaning is quite clearly the same if you ask a human, but in terms of the Python syntax, something slightly different is going on, although the result ends up being the same. So, by the way, also I want to note that if you do a equals numpy zeros 2, 3, then this doesn't work. So the numpy zeros and also the numpy 1's functionality, it requires the dimension to either be 1 dimensions, and if the dimension is just equal to 1, then you're allowed to provide just one number. But otherwise, if there are more than 1 dimensions, you are required to provide all the dimensions in tuples. If you just write 2, 3, then the NumPy library will interpret this as the input that corresponds to dimensions, and then it will be confused about this second input. Okay. Now, this notation is somewhat unfortunate because, so the NumPy module has a random submodule, and the random submodule is used to provide features for generating random numbers. So let's take a look at this example. So NumPy random rand 4, 2, this creates a 4x2 NumPy array, all populated with random numbers between 0 and 1. All the numbers are uniform, has a uniform distribution between 0 and 1, and they are, of course, IID, independently distributed. So every time I run this, the result is going to be different. And all the numbers are going to be between 0 and 1. The dimension is 4, 2. Now, but this is slightly unfortunate because there's a notation inconsistency. So here we have 4, 2, and so we're just providing the 2 dimensions as just inputs without, as separate inputs, rather than providing them as a single tuple input. If we were to write things in a consistent way, and instead write 4, 2, then this would result in an error. So when you're using the 0 function and the 1 function, and you want to provide multiple dimensions, you need to provide a tuple. When you use the rand function, then you must provide the dimensions separately. If you want to have another dimension, then if you want to have another dimension, then you need to provide the third dimension just separately. So this is an unfortunate inconsistency, but it is what it is. It's not my fault. Okay, if you want to create, so this first command creates random numbers between uniform random numbers. If you want to create random normal numbers, so if you want to create normally distributed random numbers, this is how you do it. So here I provide just dimension 5. If I want multiple dimensions, again, I need to specify them just separately as separate inputs rather than providing a single tuple input. So having a single tuple input doesn't work. You need to provide them as separate dimensions. Okay, and if you want to provide random integers, then the way you do this is you provide, if you want to create random integers, so here we're generating random integers, in this case a 3x3 matrix, and we're specifying the range -4 inclusive and +8 exclusive. So as you can see in this generation, the number +8 never gets generated because the endpoint by convention in Python is excluded. In this case, the notation is different, so we specify a size with a keyword argument, and we provide the size as a tuple. So this is all inconsistent, and it's a bit unfortunate, but again, it is what it is. So when you're using these NumPy functions to create arrays, you will have to, because yes, if you use these features for long enough, you'll get to remember. You'll eventually remember the individual syntax in terms of how to provide the inputs. But as a beginner, you won't remember them. And to be fair, you shouldn't be expected to remember how these inputs work. So you'll have to be looking up how the inputs should be structured for each individual functions whenever you use them. So in NumPy, you can create the identity matrix with the identity function. So np.identity, this creates a 2x2 array, in this case with dimension. This creates a 5x5 array, a dimension 2 array with the ones in the diagonal. Okay. So, and by the way, the notion of identity is reserved for, it's the thing that you have for matrices. So this command is used to exclusively create two-dimensional arrays. Okay. So if you want to create a NumPy array with that looks like this, so numbers 1, 3, 5, 8, or maybe I want to have them spaced by 1, you use the NumPy arange. So this is pretty much the same. This is similar to the range function, the Python intrinsic range function that we had seen before. Now the difference is that range returns an iterable, and while a NumPy arange returns a NumPy array. And the idea behind the name arange is that it's like the method, it's like the function range, but it's for array. So the name is short for array range. It's unrelated to the verb arrange. So I clarify that point just to make clear that this has nothing to do with like reordering or making something more clean. Right? It's just it's creating an array like the range function, a NumPy array like the range function. Okay, so reorganizing. So that's done. Let me tell you how to do that, since that came up. Okay, so here first, let's create a NumPy array from a nested Python list. So this will be a two-dimensional NumPy array, right? So it's a 2x4 NumPy array. So shape, it's 2x4. The number of dimensions is equal to 2. Now, if I want to preserve the same entries, but if I want to reshape the array into a different shape, then the elements are 1, 2, 3, 4, 5, 6, 7, 8. But this is a 2x4 matrix. If I want to reshape this into a 4x2 matrix, then I call the method reshape with the object a, and I provide the dimensions as a tuple. By the way, the number of dimensions need not be the same, so I could do 2x2x2. So the number of elements need to be preserved, but the dimensions, they don't have to be the same. So this way, this 2x4 array, which contained 8 elements, has now been reshaped into a 2x2x2 array, which also has 8 elements. When you're using these reshape operations, it's quite often useful to not worry about a certain dimension. So let's say if I want to reshape this 2x4 array into a 4x whatever. So in this case, the calculation is very simple, right? The original is 2x4, so if we're going to shape it into 4x whatever, this value has to be equal to 2 in order for the number of elements to exactly fit. But sometimes the calculation is not clear. Maybe you'll have to spend 10 seconds to think about it. So it's just more convenient to not specify one dimension, a single dimension, in which case you would just write -1. If you write -1, then this becomes whatever it has to be so that the shape is going to fit. So for example, if I write 8, 1, then the remaining dimension, it has to be 1. If I write 2, -1, then the other dimension has to be 4. If I write 1, -1, the other dimension has to be 8. And if I write 3, -1, then it's not going to fit. There's no possible other dimension to make this fit, so we're going to get an error. Okay, we can also do this with more than 2 dimensions, so the number of dimensions is changing, but in case this last dimension is automatically inferred to be equal to 2. Okay. Now here in this example, we have two arrays, v1 and v2. Both are of dimension 1. Now we can do what's called so here the vertical stack approach, a method will stack these two NumPy arrays vertically. So this array is understood to be like a row vector. This is also understood to be like a row vector. So the vertical stack operator it ends up creating a 2x4 array. And well, since we have a v stack, we should of course have h stack corresponding to horizontal stacking. So here h1 is let's print out h1, print h2. So here h1 is a 2x4 matrix, h2 is a 2x2 array. So if we stack them horizontally, then we get the first part and then the h2 stacked thereafter. Now when we do the stack, we can provide the things to be stacked in a tuple, or we can also provide them in a list. So here I'm providing them as a list. That's perfectly fine. But here I'm providing them as a tuple. And that also works just fine. Now if I were to change this to a v-stack, then this of course wouldn't work because the dimensions don't fit. So this one has to be h-stack. But in the previous example, this can be stacked horizontally. So if I change this to h-stack, then this works just fine. We still, then in this case, after the h-stack, we have a one-dimensional length 8 NumPy array. So next is the notion of vectorization. So this notion might be familiar if you have used, let's say, the language MATLAB a lot, but I'll explain. So let's take a look at this example. This is an example where we have not vectorized anything. And this is a reasonably Pythonic way of plotting the function sine x, but we're not using the module NumPy. Okay. So what we will do is we will create, first let's just look at the plot. So the plot looks like this. This is the sine function. And to plot this, we're using the matplotlib pyplot module. So I'll talk about this more soon, but for the moment, we can just view this as, so here's where the plotting happens. It's just a library that allows us to plot things. And what we're doing is we are creating an x array and a y array. So if I print out x, it's hard to see, but this is the numbers, the points that we have on the x-axis. And if we print y, those are the corresponding y values, the evaluation of sine x. So the x array, x is a list containing numbers between 0 and, in this case, 4 times pi. And then the way we create this is we created this array via list comprehension. So list comprehension is a very Pythonic thing, isn't it? So we have this thing that we're going to evaluate for I within range of n. So I will start from 0 and it will go up to n minus 1. N is excluded. And then we will evaluate these values. So note that this is a constant. The I is the number that is being changed. So we have points with uniform spacing of this much, and I will be incremented by 1 for all the elements in this array. So once we create this array, now then we also want to create corresponding y values. So then what we do is for all xi, so this is the I sort of x point, for all xi within our array x, we evaluate math.sinexi, and then we create an array, again with list comprehension. So x and y, the two arrays were created with list comprehension, and then we plotted it. So this is fine. You can do this, especially if for some reason you don't want to use NumPy. But this is, in my view, this list comprehension is quite clean. It's much cleaner than just using a raw for loop. But it's still not the most readable thing, in my view. I think the following example is a more readable, results in a more readable code. And also this code is a little bit inefficient in the sense that this code is really fast, so it doesn't really matter. But if you were to do something like this with a lot more points, with a lot more computation, this type of list comprehension is not the most efficient thing in terms of the execution time. So the better way to accomplish this is to use a NumPy, and when you use NumPy, we can avoid the use of loops and list comprehensions altogether. So, and the way we do that is we vectorize our operations. So to do so, we import the library NumPy, and then first we create the x. Now in this case, x is no longer a list, x is now a NumPy array. So we print, let's say x. So the x array looks like this. And now at NumPy, the number of dimension, is equal to 1. The shape of x is 100, nothing. And when we created the syntax for creating this x array, I think it's much more clean. So we are using the linspace, the linear spacing function of the NumPy module. We specify a starting point, we specify an ending point, 4 times pi, and we specify the number of points to have within this range. And then next we'll just plot it. So we'll plot x and then NumPy sin x. So this is what's called a vectorized operation. When we do numpy.sin, so x is a NumPy array. And the sin function, usually, the way we understand it, is it's a scalar valued function. We provide in a number to the sin function, and out comes a number. The sin function is usually not defined, at least mathematically, it's not defined for vector inputs. So the way this is understood is that the sin function is evaluated for all the elements of the NumPy array x, one at a time, element-wise. And this is example of a vectorized operation because x is like a vector. It's an array, but it's like, and we can also interpret it as a vector. But in any case, it's an array, and this function is applied just as a whole to the array. So this is much more, in my view, a cleaner execution of plotting sin of x, and it's certainly, if you were to measure time, it's actually more efficient in terms of the running time. By the way, in order to perform these vectorized operations, it's necessary to use the NumPy sin function because the math.sin function, so if we import math, the math.sin function, it doesn't work because the math.sin function is designed to take in as input just a regular number rather than a NumPy array. So to perform this vectorized operation, we need the sin function implemented by the NumPy library. So the NumPy library and the NumPy functions more specifically allow us to perform vectorized operations. Now, conversely speaking, if you're using NumPy objects, and if you find yourself iterating through a NumPy array, so maybe you're using a for loop or maybe using a list comprehension for the individual elements of a NumPy array, then there's a good chance that you're actually doing something wrong. So vectorized code is much more shorter and fastable and often more readable. So whenever you catch yourself writing a for loop, iterating through the elements of a NumPy array one at a time, you are probably doing something wrong, and you should spend some effort to look for ways to perform the same operation, but in a vectorized way. And this type of vectorization does take a little bit of getting used to. So when you're first starting out using the NumPy library and the PyTorch library, it can take you it will take you a little bit of extra effort to figure out vectorization, but it's going to be worth it. So to reiterate this point again, the principle of vectorization applies to all NumPy arrays, not just a unidimensional array, but multidimensional arrays. For multidimensional arrays, you can also use vectorization as well. You are encouraged to use vectorization as well. But the name ArrayRise, it's hard to pronounce. It doesn't feel very good to say it. So that's why people say vectorize instead of like ArrayRise. And also the word vectorize has been in use in other languages, such as MATLAB, for example. So it was an existing terminology, so it was just adopted for use in NumPy as well. The next notion I want to talk about is broadcasting. So arithmetic operations on NumPy arrays of the same size are by default performed element-wise. So here's an example, NumPy array range 7, So if we compute x times x, you might, at first sight, you might expect this to come out as a result in the inner product, but that's actually not the case. By default, arithmetic operations are performed element-wise. So here, instead of getting the inner product, we get all the elements squared. However, when we have arrays of different sizes, then the smaller array is what's called broadcast across the larger array, and then the arithmetic operations are carried out that way. So in some sense, the broadcast generalizes the outer product of vectors. So let's take a look at an example. So here we have x is numpy a range 5, y is numpy a range 6. So, and by the way, so we're performing this assignment with tuples. We print out x, this is what x looks like. If we print out y, this is what y looks like. If we try to add these two, then, well, I mean, this shouldn't work, right? And it doesn't work because the dimensions, they don't match. But if we instead do this reshape, so let's do this reshape, and let's do this reshape. So let's first see what this reshape does. So this reshapes the array x into a 2D array with dimension, in this case, 5, 1. So this dimension 1 is specified, this minus 1 is left to be inferred. The total number of elements is 5, so it has to be a 5 by 1 2D array. That's the result. Here we reshape the y array into a 1 by whatever dimension. So since there are 6 elements, the result becomes a 2D array of dimension 1 by 6. Now these two 2D arrays can be added. At least they can be added when we use broadcasting. Or let me keep this. Okay. So when we perform the addition, this is x plus y, or at least the reshaped versions of x plus y. And now this result comes out to be this thing. And the result can be understood in this way. So the 0, 0 coordinate is this 0 plus 0. And the 0, 1 coordinate is 0 plus 1. The 0, 2 coordinate, 0, 2 coordinate is 0 plus 2. And let's say this coordinate is 1, 3. Sorry, this coordinate is 1, 2, so that's 1 plus 2, that's equal to 3. And then this bottom right corner, that's 4 plus 5. So again, this notion generalizes the outer product of vectors. So if we do use addition in terms of multiplication, that's actually exactly what we have. In this case, we have the outer product of x and the vectors x and y. And the NumPy library actually has an explicit outer product function, and the result is exactly the same. So here I showed you an example of broadcasting with two arrays, but actually the most common form of broadcasting is with an array and a scalar. So here we have NumPy a range of 5, so this creates a NumPy array with elements 1, 2, 3, 4, but then we add the scalar here. So a scalar plus a vector, what does that mean? Well, mathematically, you're not allowed to perform a scalar plus a vector, but in the NumPy library, this is understood to be the arithmetic operation is to be understood to be performed in a broadcasted way. So all the elements of so we take all the elements of this array and then add the number 5.5 to it. We can also perform this broadcasting with scalar times array. So here we have a 3 by 3 array, all containing the values 1. We multiply 3.5, so all the elements become contain value 3.5. And because this operation, so this can be understood as a scalar times matrix product, because this operation is permitted in just regular math, regular linear algebra, one might consider it to be quite natural, but I think the proper way to understand this is to view this as a special case of the broadcasting operation. Next, let's talk about how to index elements of a NumPy array. So you can access elements of a NumPy array with direct indexing and slicing. So direct indexing is just providing an index directly, and slicing is using the slice notation as we had seen with lists. So these indexing methods we are already quite familiar with because we've seen them with Python lists. But there are other approaches. So the other approaches are advanced indexing and Boolean masks, and we'll see how those work as well. So first, let's take a look at a simple example. So A is created to be a random is created with the random rand_n function from the module np.random. So this is a 10 by 10 matrix containing standard random normal variables. So it looks like this. The whole array, the whole 2 by 2, the 10 by 10 array looks like this. We can access the 4 by 5th element just directly, so this is direct indexing. We can also perform slicing. So this is a 2D array, so we need to provide two indexing inputs. So here the first indexing input is 1:8:2, so that means we will be accessing the first, the third, the fifth, and the 7th row of this matrix. So it's from 1 up to 7, 8 excluded, and with a step of 2. So that's the slice notation that we had seen before. And then we're extracting the 7th column. Now, so here we extracted the from the 7th column we extracted the first, the second, the third, the fifth, and the 7th element, and the result is a 1D NumPy array. But we can also extract multiple columns if we wanted. So we can use slicing on both dimensions as well if we want, and the result will be a 4 by 2 2D NumPy array. Okay, so then before we move on to other indexing options, I want to make this quick note. So when you copy NumPy arrays, you want to be very careful. So for the sake of efficiency, NumPy operations often avoid copying data as much as possible and rather provide different views of the shared underlying data. So here's what I mean. Okay, so all right, so here we have a NumPy array. So X is a NumPy array, and then X with this slice notation. So this creates a different view of X, of the data associated with X, rather than creating a copy of the data of X. So here, if I print X, then, well, it's just this thing. But then if I print Y, it's actually the same thing. But what I mean is that, what I mean when I say this just creates a different view rather than a copy, is if I do a loop and assign all values 0 to the Y NumPy array, actually the change is observable from the X array as well. So the data, and of course if I print the value of X over here, the value is 0, 1, 2, 3, 4. So this assignment using the Y array, the Y NumPy array, affected the data associated with the X array as well. And this is when you're working with Python lists, this is often the common approach to creating a copy, but that doesn't work with NumPy arrays. And this also is the case where we have a subset of the elements. So here from the NumPy array X, we extract from the elements 2 and 3, and we have that be the Z array. So if we print, let's say here, if we print Z, then okay, let me get rid of this. If we print the Z array, the elements are 1, 2. If we probe the type of the Z array, Z is a NumPy ND array, Z.NDIN, so it's a 1D NumPy array, Z is. And then if we do this, by the way, if you were to if you were trying to write an inefficient code, this should have given you a red flag, because here I'm iterating through with using a for loop elements of a NumPy array, and that's usually bad. You want to vectorize our operation. So here is a vectorized write to all the elements of Z. Here the write is just broadcasted, so for all the elements of Z, we assign value as 7. And then if I print X, now the value of X has been changed. So the data associated with X has been now modified. By the way, here's a quick question. If I do this, what do you think is going to happen? I'll let you think for a second. The answer is this. And to give you a hint as to why that happens, so that's the output of Z when I do this. Whereas if I have the slice notation, this is the output. So I'll let you think about why there's a difference in the behavior when I remove the slice thing. Okay. Okay. Now this behavior contrasts to what we see when we have lists. So here x is defined to be a Python list containing these integers. Now this operation is commonly used to create a copy of the array x rather than getting whatever different view or whatever, something like that. So here, if I modify the elements of the array in y, it doesn't affect x. And by the way, this type of broadcasting right is not allowed for lists. So the notion of broadcasting is not something that is used universally across in Python. Rather, it's something that is used in the NumPy library and also the PyTorch library, which we'll talk about soon. Okay, so when you create NumPy arrays, when you sort of try to copy NumPy arrays, often it will try to avoid making copies for the sake of efficiency. So if you want to explicitly, if you really want to have copy data, you want to be explicit and use the copy method. So here x is a NumPy array, and if I do x.copy, then now it doesn't matter how I change y. So here if I print y has been all assigned to be 0, but x and y now refer to distinct NumPy arrays with distinct associated with different distinct associated data. So changing y now doesn't affect x. So next, let's talk about advanced indexing. So in advanced indexing, you pass in a list of NumPy array indices to access the elements. And this is a thing. Advanced indexing is something that doesn't work on Python lists. So okay, so let's take a look at an example. So here's what I mean. All right, so NumPy a range 5. So that creates a 1D NumPy array of length 5 that looks like this. Now, if I want to access the first element and the fourth element, then what I can do is I can provide as input into this bracket operation the list 1, 4. So this gives me, and maybe I'll do, let's try this. So this gives me the NumPy array with elements 1 and 4. So remember, print x. So this is the first element, this is the fourth element, and that's what we see. Now to clarify, this thing won't work. And why wouldn't this work? Well, because this is indistinguishable from trying to access element 1, 4, right? So this is as if, so this can be interpreted as we are viewing x as a 2D array, and we're trying to access the element in position 1, 4. But x is a 1D NumPy array, so providing 2 indices is not okay. So when we want to use the advanced indexing, we need to provide as input a list. So this is a raw Python list, or we can provide a NumPy array of indices to access those elements. Now, something like this can be utilized in this kind of cute way. So here, A is just some matrix. So we create a 1D array with NumPy a range, and its length is 24. So it contains elements from integers from 0 to 23. And then we use the reshape operation to reshape into a 4 by, in this case, 6 2D NumPy array, which looks like this. And then we extract the column dimension. So by looking at this, we know that it's 6, but the way we extract it is we a.shape, that's that. So a.shape, that returns the shape of our NumPy array. It's 4 by 6. It's a tuple containing 4 and 6. If we access so this is the 0th dimension. If we access the first dimension, we get the value 6. So a.shape1, that's 1. So we create NumPy a range of this. So this is a NumPy array containing values 1, 2, 3, 4, 5. And then we get a random permutation of that. So this is what's printed is a random permutation from 0 to 6, and it's different every time we execute it because it's a random permutation. And then we write that into this variable perm. So perm refers to this random NumPy array with 0 to up to 5 randomly permuted. So let's print this out. Yes, so every time it's different. And then finally, here we're using, for the first index, we're using the slice notation. For the second index, we're using the advanced indexing. We're providing a NumPy array to access the columns in the order specified by this perm NumPy array. So the result of this is that, so this is the order in which we'll be accessing the columns. And when we do so, this is the result. The result is that the NumPy array A, which originally had a determined structure, now we are randomly permuting the columns of X. So every time we do this, the contents of each column remain the same, but they are permuted randomly. Okay, so this is in my view, a pretty cute exercise of how to performing permutation of the data, in this case the column of a given NumPy array, using advanced indexing. So the next indexing technique is Boolean masks. So with Boolean masks, you pass in a list or NumPy array of Booleans that have, and the list or NumPy array that has to have the same shape as the NumPy array that you're trying to access, and the value of the Booleans will determine which elements you access. And by the way, Boolean masks don't work with Python lists. Okay, so let's take a look at an example. So here, this is a command that affects how NumPy arrays are printed when we use the print command, but there's no need to worry about this. This command sets the random seed used by NumPy random, but for the purpose of this example, you don't have to worry about this. So just ignore these two commands if you don't know what they are. Now, okay, so let's take a look. We create a random NumPy array. So it's a NumPy array with, it's a 1D NumPy array of length 5 containing random normal numbers. So it comes out that some of them are positive, some of them are negative. If we print X, this is the result. Now we can create a mask using actually a broadcasted operation. So for each element within the array X, so this is a vectorized, this is a broadcasted operation. So for each element of the NumPy array X, we will compare the result with value 0. Okay, so and then let's print out the result. So the result of this operation is a NumPy array containing booleans. So is X bigger than 0? Well, it's bigger than 0 for the first one, so it's true. For the second, for the 0th one, it's true. For the first, the second, and third is false. So false, 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 and for the last one, it's true. So if we look at the type of this this mask, it's a NumPy array. So if the number of dimensions, it's 1. It's a 1D NumPy array with data type bool. It's a NumPy array with Boolean data types. Okay, so we have true, false, false, true, and now this is the Boolean, the use of the Boolean mask to perform indexing. So when I print this, so the mask indicates, now when we provide the mask within the bracket, what the mask does, it indicates which elements should be extracted in this indexing. It tells us that we should extract this element, we should extract this element, but these elements should not be extracted. So the resulting the result of this print is that we get 1.62 and 0.87. So this is an example where we use Boolean masks to extract elements and read them, right? So we are printing them out, so that's a read from this NumPy array X. But we can also perform a write as well. So here the mask tells us which elements to extract, and then we're performing a broadcasted write to those elements. In this case, we have 2 positive elements, and we assign the value 0 to all of them. And then the effect of this is once we print out the vector X, the values of 0 that were positive are assigned to be 0. Now another more concise way to do this is this would be exactly the same thing, is X bracket X bigger than or equal to 0 is equal to X. So this would achieve exactly the same effect, but in a more concise way. So sometimes when you're using Boolean masks, you may have more than one mask, and in that case, you may want to combine those Boolean masks using logical operations. Now the Python language usually comes with the logical operations, let's say and or, innately within the Python language, but these native logical operators cannot be used on Boolean masks for some reason in the NumPy library. So in order to perform logical operations, you need to explicitly use the NumPy versions of these Boolean operations. So here is an example of x, some array x, and we have one mask, here's another mask. So we have here's one mask, here's another mask. And if I want to combine these element-wise using the AND logical operation, we need to use the numpy.logical and then provide the two inputs. That way we get this result, which is the result of applying logical AND. And if we want to, let's say, apply the XOR operator, then we need to use the numpy.logical XOR function, provide two masks to get another mask with the XOR operator applied element-wise. Next, let me tell you how to do linear algebraic operations in NumPy. So in NumPy, matrix multiplication and, in fact, more generally, linear algebraic products are performed using the @ symbol rather than the star operator. So the @ operator is the linear algebraic products. Let's take a look at an example. So here we import NumPy as NP, n is some dimension, A is as an n by n matrix, and B is a length n array. And well, to be more precise, A is as an 2D n by n NumPy array, and B is a 1D length n array. But we can interpret this as an n by n matrix, and we can interpret this as a length n vector. Now, if we do A times B, then what happens is this is in fact a broadcasted product. So this is actually not the matrix vector product, and as you can see, the result is, well, if you meant this as a matrix vector product, the result should be a vector, not a matrix, but you get a matrix. So it's an interesting exercise to figure out why it is exactly, how the broadcasting is exactly working to produce this result, but we'll not spend time on that. We'll just point out that this is not what you want if you are aiming to perform a matrix vector product. Rather, if you want to perform this linear algebraic matrix vector product, then you do write A at B. And this gives us the matrix vector product. The reason I say that this is a linear algebraic product rather than matrix multiplication is because, so if we have B times B, then this is just understood as element-wise product because all algebraic operations on NumPy arrays are by default performed element-wise or broadcasted. So this is just element-wise product. But if you want to perform the dot product, which is a more linear algebraic operation, then use the @ symbol, and this gives you the dot product. If you have a matrix, then you can perform the transpose. You can access the transpose by calling the transpose method or by accessing the attribute T, capital T. Okay, so here if I have A is a 4 by 7 matrix, B is a length 7 vector, then we can perform this product A at B that will result in a length 4 vector, and then we can perform the product A transpose times that length 4 vector. So this comes out to be a length 7 vector. The numpy.linalg module, linalg is of course the abbreviation of linear algebra. This module provides other linear algebraic functions. So for example, if you want to compute the determinant of a matrix, then well, linalg has that. If you want to compute eigenvalues, linalg has that as well. So other more complicated linear algebraic operations, most of the standard ones that you would find, most of the standard things that you would find in a basic linear algebra textbook, they're all available in the numpy.linalg module. Okay, so that's it with the discussion of the NumPy library. Next, let's move on to talking about the matplotlib library. So the matplotlib and pyplot library is a Python library used to create plots. And I imagine most of you who are listening to this tutorial would likely find the matter of plotting a rather dull affair. There's really nothing intellectually challenging or exciting about creating pretty plots, and I would agree. I don't personally consider plotting to be a very exciting subject, but it's a very necessary component of doing science. So my goal is to provide you a quick overview of how this library works, and my hope is that by you listening to this tutorial, you'll be saving time compared to the alternative. And the alternative being not explicitly ever learning about how this plotting library works and just trying to search plotting code whenever you need it. So that's hopefully spending a few minutes to learn about it. This will save you time down the line. Okay, so matplotlib and pyplot, it's used to plot data contained in raw Python lists and also with NumPy arrays. So the library explicitly interfaces with the NumPy library. And in the most basic form, a plot is basically just a line sequentially connecting points on the 2D plane. To display plots on Jupyter Notebooks, you want to use the so-called magic matplotlib inline. So I won't explain really what this is, but just use it. So whenever you're importing the matplotlib.pyplot module, and when you're doing that within a Jupyter Notebook, then just run this. Okay, so let's take a look at an example. So here we imported this module as PLT because indeed this is a rather long name. We don't want to be retyping this long name every time we use the module, so we abbreviated that to PLT. We execute this magic command, and now we plot this this data. So these are the x-axis for the data points, and these are the y values. So we have 0, 5, we have 1, 9, we have 2, 3, and then 3, 2. So there are 4 points, and the plot is a line sequentially connecting these points. Okay, so to create this kind of plot, you provide the x values, you provide the y values in lists of the same length. So if the length of the two lists don't match, then that's not okay. The two lists or NumPy arrays, the lengths have to match. And the command is plt.plot. So this command creates the plot, and plt.show. This is to be executed after the plot has been constructed, and that will display the plot. Now the reason you want to have this command executed explicitly after you create the plot is because sometimes a plot can have multiple components. So here's an example. You have multiple curves on the same plot. So let's just execute this first. So here's one plot, and here's another plot. So the way we do this is we just plot multiple curves separately. And in this case, the pyplot is smart enough to know that, okay, we should use different colors for these two curves, and indeed that's the case. And then after all of the elements of the plot have been constructed, then we do the show. And the reason we want to do this is, if we were to do this, well, in this case, the whole thing is, so what happens is we first created this plot and then we showed, and then after that we tried to add additional things, and that's not good. So in this case, the plot gets split into two. So after everything is constructed, once everything is ready, you then show the plot. So there are many ways to fine-tune the visual of the plot. So let's take a look at this example. So in this plot, the input data ranges from -2 to 2, but maybe you want to focus in on a more narrow region of this plot. So one option is to modify the data so that the input ranges from -1.5 to +1.5, which is the range that we desire. But often we don't want to change the data if we're just trying to fine-tune the visualization. So what we can do is we can specify in a list. So we use the axis function. We provide a list containing the limits. So xmin, xmax, ymin, ymax. So that limits the x range and the y range of this plot. Okay, so all right. Okay, it's also possible to label your plot. Okay, so here, this is the same example as before. This is the x data. We plot cosine. We plot exp. And by the way, this is a vectorized. This is vectorized NumPy code. We limit the axis with these xmin, xmax values. We can we provide a label for the x-axis. We provide a label for the y-axis. We provide a plot title, and we also provide a legend. So this is the cosine x function. This is the exp function. Now here, the way this legend function worked was that we had two plots. And internally, the PyPlot remembers the order in which these plots were constructed. So the cosine plot was drawn first, and then the x plot was drawn second. And then when we provide the legends, there's the first string, there's the second string. So PyPlot remembers the order and matches, okay, so this is the first string, this was the first plot constructed, this is the second string, this is the second plot that was constructed. So PyPlot internally remembers the orders and matches, and that's how it matches the legend with the plot. But that's a little bit inconvenient, because if for some reason I accidentally change the order of the plot, now the labeling is no longer correct, because it says blue is the cosine function, but this is the exponent function. It says orange is the exponent function, but that's the cosine function. So this is a little bit, this is not ideal. So it's actually better to specify the legends via keyword arguments. So for each plot, instead of using so now in this example, we are calling the function legend, but we're not providing any inputs. We're just saying a legend should be created. So then if we're just saying a legend should be created, then what should the legend text be? So by the way, this box labeling each curve, this is called the legend, a legend in the plot. So we're not specifying the text that should go into the legend. Well, that's specified over here. So for this plot, we're specifying the label. The label for this function should be cosine x. The label for this function should be x. And then when we plot it, well, now the text is accurately matched with the plot. Now, if I change the order in which these are plotted, actually the order of the legend will be changed. So the order of the legend will still correspond to the order in which the plots were created. But now, because the label is attached to this plot function, there's no risk of a label being misattributed to an incorrect plot. So when you create these curves in PyPlot, you can specify the line styles with format strings. So in this previous plot, I just plotted the curve, and it just became a smooth curve, and the color was assigned automatically. But you can control those things automatically, manually. Now the way you do this is with format strings. So let me show you an example. So here's this first plot, and let's just have this for the moment. Okay, so here here's the format string. It says that the color should be red, there should be no line, and the marker should be a cross. So here we have 4 points, and there's no line, we just have cross markers. Here's the second plot. It's saying that the color should be blue, the line should be this dotted line, and the markers should be the circle. So another possibility is if I remove the marker, then it's possible to have no marker. If I just specify one line, that's just a straight line. Here are some other examples. So this is actually with the same data, but so here the color should be red, and the line style should be this dotted line. And this says that and here I'm not specifying a marker style. If I wanted to, I could have the marker style be whatever. It could be other things. In any case, and then this here this format string is saying that the K stands for black because B is for blue, so black can't be B, so K is for black. So this is saying that the color should be black and the line should be of this style. So this is how commonly line styles are formatted. If you want to know more about how to form these format strings, the precise rules, you can go to this link, scroll down, and then here is a description of how those things should work. If you're interested, you can read the details. So this formatting string is concise. It's very concise. It's standard. So if you read other people's code, you'll encounter this all the time. But in my view, in my personal opinion, I don't think this is very readable. So I think the better, more Pythonic way is to use keyword arguments. By the way, this syntax I think is inherited from the MATLAB programming language. It's a more older style of specifying plot style information. But I think the better, the more modern approach is to use keyword arguments, quarks. So here in this example, we have 3 plots, and we can specify the color. And in this case, I can specify also colors in RGB hex code. So this is actually, this corresponds to this color. This is actually the SNU blue. So here we can spell out the color green, or we could write just G for green, B is for blue, K is for black. So you can use these abbreviations if you want, but I think it's just kinder to write out these color names with an English word. So yeah, so you can specify the colors with keyword arguments. This is also another hex code specified color. So if you know what hex codes are, then you know what this is, but this is just some way of specifying the color of the line with an RGB value. You can also specify the line style as a keyword argument, and if you want to have a marker, then you can specify what marker you want to use. So this use of kwargs, in my view, is a much more readable and Pythonic way to specify the style. And if you want to specify other plot properties, you can do so with keyword arguments. So here I'm specifying the line width of the first plot to be 4, and I can also specify the size of the marker. So there are many plot properties you can specify, and you can do so with keyword arguments. By the way, what this is this code is equivalent to just this, but in some cases you may want to have a single Python expression span multiple lines because there are just too many options in this function. In which case you can write backslash and on this computer, because I have a Korean Windows operating system, the backslash character is rendered as the 1 symbol. But in any case, if I have this means the line break should not be interpreted as a line break, rather it's just text continued on in the next line. Okay. Now, when you plot lines are layered in the orders that they are added. So here I draw the red line and then I draw the blue line. And in this case, the line widths are, lines are thick, so the intersection actually is visible, and you can see that the blue comes on top of red. But if you do this, then now red comes on top of blue. So in this case, the order does matter. If you want to change the font settings of your plot, you can use the plt.rc command. So rc is a old but standard abbreviation in programming for runtime configuration. It's not a very good name from a modern from a modern view of naming functions, giving good names for a function. But it's an old convention. So here, when we render the text in our plots, I'm saying I'm going to use tech. So tech is a thing that allows us to render mathematical equations. When I do that, I can have like sine x, sine squared x, and then the sine squared x will be rendered in this nice math way. A transpose x, is now rendered in this nice way. I have this norm symbol squared. So if I want to typeset math equations within my plot, I can use this command. I change the font family to serif. I change the size of the font. So you can change these font settings using the plotrc command. So here I made some changes, but if I want to revert the changes to just the default setting, I'll just do plotrc defaults, plt-rc defaults. If you want, when you create a plot, if you want to have grids in the background, you can use the plt.grid command. And if you're unhappy with the default style, but if you don't want to spend time customizing your plots, then you can use one of the available other styles. So let's take a look at this for the moment. Okay, so from the module plt, we can print out plt.style.available. This gives us a list of available styles that we can use from. Okay, so first I'll just revert all the RC changes that I have made, and then I'll choose to use, let's say, ggplot. So ggplot stands for the grammar of graphics. So Leland Wilkins Grammar of Graphics. This is a this is a famous book by a statistician, Leland Wilkinson, and so he has he has strong views as to what's the best way to draw plots and visualize data. But the ggplot style incorporates Leland Wilkinson's sort of approaches. And this is what the plot looks like. Okay, so here, aside from claiming of choosing ggplot as the style that I wish to use, otherwise I just plotted the data and then provided labels. I had a legend, and that's it. And now the plot comes out to be a completely different style compared to what we had before. And you can have opinions as to whether this is good or not, but it's a different style. And if you want, you can try other styles. So this is a Seaborn notebook. Let's see. Let's do 538. Okay, so then once you've finished drawing your figures, then if you want to save your figure, then you can use plt.savefig. Okay, so here we create a plot, and instead of showing the plot, I'm just going to save the figure. So in this case, even though I don't do plt.show, the plot ends up showing on the Jupyter Notebook due to this match command. But in any case, the point is that the figure has been saved to plot.plt. So this Jupyter Notebook is saved on the desktop of this computer. It's being executed from the desktop of this computer. So if I go to the desktop, here, this figure, this plot has been generated. So to show this to you again, let me delete this. And let's do a plot test. Okay, so I execute this command, and as you can see, the plot.test PNG file has been created. Next, PyTorch. So throughout this course, we will be learning the PyTorch library more in depth as we learn the relevant deep learning concepts. But for the moment, let's very briefly discuss it. So the PyTorch library is fundamentally a numerical computation library rather than a deep learning library. Throughout this tutorial, I have myself called PyTorch a deep learning library, and that's what most people consider it to be. But fundamentally, the design goal of the library PyTorch is to provide a numerical computation library that is superior compared to NumPy. PyTorch shares a lot of similarities with NumPy, but what makes PyTorch suitable for doing neural network computation and machine learning are the following three key properties. So the first is PyTorch supports easy GPU computation. So nowadays there are some libraries that help to translate NumPy code into a GPU computable code, but for the most part, NumPy was designed with CPU computation in mind, whereas PyTorch is designed with GPU PyTorch was expressly designed to support GPU computation. A second key aspect of the PyTorch library is that it supports automatic differentiation. So this is a feature that we will be utilizing extensively throughout this course, and we will also explicitly talk about this at some point. Finally, other people. There are a lot of machine learning libraries and sample code out there on the internet because other people use PyTorch a lot for this purpose. So other people have used PyTorch to do deep learning. That generates a large body of sample code that's made available on the web. So because other people use PyTorch for machine learning, it's easier for us to use PyTorch for machine learning. So you should think of PyTorch as a replacement for NumPy. As a quick aside, in PyTorch, the terminology tensor is used rather than array. So in NumPy, an array is an object, is a collection of elements, usually numbers, that can have dimension 1, 2, 3, 4, and even higher. And the same is true with tensor. So a tensor can have dimension 1, dimension 2, dimension 3, and higher. Okay, let's start using the PyTorch library. So we'll import the NumPy library as NP, and we'll import the Torch library as Torch. So it is customary to import NumPy as NP, but it is customary to import Torch as is without a shorter alias. So the first thing we can look at is the Torch version installed on this machine. So if I run this, it says that the Torch version on this machine is 1.5. And this indicates that I installed Torch on this machine quite a while ago because the most recent stable version of Torch is version 1.9. Okay, so let's first create an array in NumPy. So here we create an array in NumPy. and it's the 0 array as 2 by 3 0 array. So to create a 0 array in PyTorch, the syntax is very similar. So we call the function torch.zeros instead of numpy.zeros, and that gives us a torch tensor rather than a numpy array. And there are some slight differences in the syntax. So when you look at the attribute shape of a NumPy array, it gives a tuple containing the dimensions. If you extract the shape of a torch tensor, the shape comes itself is returned as a torch size object. So the way you use NumPy torch tensors is similar to NumPy arrays. So here we had this NumPy 0 array, so the 0, 1th element can be accessed just with regular indexing. Here we can access the 0, 1th element of this PyTorch tensor. The result is actually a scalar valued tensor. So if you want to extract a regular number from a scalar tensor, so this is a NumPy PyTorch tensor of dimension actually 0, it's just a scalar tensor. But if we want to extract just a number, then we call the method item. So item extracts this number just as a regular Python number. Okay, so an ND PyTorch, an ND NumPy array can be converted into a PyTorch tensor. So here we have a NumPy array. We can convert that into a torch tensor. So here we have a torch tensor, and the data type is actually float64. That's indicated. And here, given a PyTorch tensor, we can extract a NumPy array by calling the NumPy method, and that gives us a NumPy array. So to be extra clear as to what the data types of these return values are, we can probe the data type with the type function. Right. So here it says this is an object of class torch tensor, and we can also do the same with this. So this tells us that the output of this output is an object of class NumPy ND array. So the terminology, the word rank of a tensor refers to the number of dimensions. So the way you can extract the number of dimensions of a PyTorch tensor is you get the shape, and then that's an array, and so specifically it's a torch size array. But in any case, you can get the length of it, and that gives us the rank of the tensor. So this is the number of dimensions of a tensor. So when you have a PyTorch tensor, you can use the method numL to obtain the total number of elements. Now, when it comes to a PyTorch tensor, you can use the method size to retrieve the size of the PyTorch tensor. This has the same effect as using a shape. But this is a slight difference between the PyTorch and a NumPy notation. So when you have a NumPy array, the shape returns, well, the dimensions, whereas size returns the total number of elements. So in NumPy, size returns the total number of elements, and in PyTorch, the corresponding method would be numL. Okay, so given a PyTorch tensor, we can reshape it with the following reshape commands. So let's create a PyTorch tensor in this way. Let's print out the values. So print t. So this so here we created a rank 2 PyTorch tensor. It's a 3 by 4 tensor. Now, as it was the case, as we did with the NumPy arrays, we can reshape the tensor using the reshape method. So here I reshape into a 12 by 1 rank 2 tensor. So this is 12 by 1. The shape is still rank. So the tensor is still rank 2. Now another option is to reshape into a 2 by 2 by 3 tensor. This is a rank 3 tensor, and as before, rank 3 tensors are kind of awkward to print out, but in this case, the rank has changed. The number of entries and this torch size object has changed. And as before, it's also possible to use a -1 to avoid specifying certain dimensions when you reshape the PyTorch tensors as well. Now, if you have a dimension of a certain dimension with length 1, then the squeeze operation is used to remove that dimension. Okay, so here we had so previously so T was a PyTorch tensor with 12 elements in total. So if we reshape it into a 12 by 1 torch tensor, then it's still a rank 2 tensor, but the dimensions are 12 and 1. If we squeeze that, then the length 1 dimension gets removed. So the result is this array, this torch tensor, where now the rank has dropped down to 1. Okay. And we can also perform an unsqueeze operation. So an unsqueeze operation is used to add a dimension of length 1. So this result, t.reshape 12, 1, that's a rank 2 tensor with dimensions 12 and 1. If we perform an unsqueeze and add the additional dimension at dimension 0, then the result is a rank 3 tensor with dimensions 12, 1, 12, 1. So in PyTorch, tensors often have the structure of batch times data. And so if the data is a 2D color image, then we'll be working with a 2D tensor of batch times color channel times x times y-axis.